Dear students, in previous lecture we have learnt about HaloAlkanes and HaloArenes, their nomenclature, preparation and physical properties. Today in this lecture we are going to learn about their chemical reactions of HaloAlkanes. Dear students, HaloAlkanes are the compounds having halogen in their structure. Alkanes with halogen. So these compounds usually undergoes three types of reactions. One is nucleophilic substitution reaction, where this halogen is going to be substituted with nucleophile, and the second type of reactions are elimination reactions, and the third elimination reactions where halogen along with beta or alpha hydrogen, it is going to be out as HX and it is going to give alkene. Elimination reactions. Then reaction with metals. Under this we are going to learn about Grignard reaction and Woods reaction. Yes students, let us see one by one. Chemical reactions. Yes, so these haloalkanes undergoes substitution reaction. What is substitution? General meaning of substitution. So whatever is here, it will be substituted with another nucleophile. Yes, in previous topic we have learned that alkyl halides, the halogen is going to have partial negative charge because of electronegativity, and whereas carbon is going to have positively charged. So this halogen will be substituted with nucleophile. So what are the common nucleophiles it will substitute? That means nucleophile will be substituted with X to give R nucleophile. For example, if I take NaOH or KOH and it is going to, for example, if the starting material is RX and if I add nucleophile of NaOH or KOH, the reacting species is going to be OH minus. This OH minus will attack onto, since it is a nucleophile electron rich compound, it is going to attack onto carbon and it is going to substitute this X group. So this X now it is going to give alcohol, alkyl halides upon reaction with sodium hydroxide or potassium hydroxide undergoes nucleophilic substitution reaction and gives alcohol plus what is left over? Sodium chloride or NaCl or KCl. So like this substitution reaction takes place. So water molecule, yes, H2O hydrolysis, it will undergo to give alcohol. So alkyl halides upon hydrolysis gives alcohols. For example, tertiary butanol upon reacting with water in presence of simple dilute acid catalyzed hydrolysis, it gives alcohol. And if I use strong base like sodium methoxide or methoxide, it is going to give ethers. And sodium iodide, if I react alkyl halides with sodium iodide, it is going to have Finkelstein exchange reaction where it is going to give alkyl iodide. And ammonia, it is going to give primary amine. So it is one of the ways to prepare amines, primary amines from alkanes, or alkyl containing amines is from alkyl halides. And if it is already the amine is primary amine, it is going to give secondary amine, it is tertiary amine if it is secondary amine. And it is very, very important, potassium cyanide if I use, it is going to be bidentate or ambident, means this carbon and nitrogen both are having nucleophiles. It can give, if I use potassium cyanide, it is going to give RCN, that is nitrile. If I use silver cyanide, yes, so this silver cyanide, silver nitrile, it is going to act as, this nitrogen is going to act as nucleophile and attacks onto alkane to give isocyanide, or it is also known as isonitrile. And in the similar manner, KNO2, potassium nitrite, it is going to give alkyl nitrite, ONO. Yes, so in this molecule also it is going to have, so this is nucleophile, it is going to attack onto alkane group, or If I use silver nitrite, it is going to act as oxygen is going to act as this nitroalkane. Nitrogen is going to act as, when we use silver nitrate, this nitrogen is going to act as nucleophile and it gives nitroalkane or NO2. Dear students, these structures are very important. Yes, in a similar manner, so silver acetate or carboxylate, it is going to give ester. Esterification it is going to take place. So alkyl halide plus this silver acetate or is going to give esters. And if I use lithium aluminum hydride in with alkyl halide, it is going to give, reduce this X group with hydrogen to give hydrocarbon, or it is going to give RH. RH, it is very important concept, students. Lithium aluminum hydride reduces alkyl halides to alkanes or hydrocarbons. In similar way, metal alkyls or metal halides, metal alkanes or MgX like that compounds, when I treat it with these alkyl halides, it is going to give alkane. For example, Wood's reaction. Under Wood's reaction, we are going to get this type of alkanes. So these are all nucleophilic substitution reaction. So the name itself says that the substitution group or the reagent what is going inside or coming inside is a nucleophile and it is going to substitute the present halogen. Yes, students. So this is how it is going to substitute halogen with nucleophile. Let us take nucleophilic substitution reaction. Yes. So it is what is happening. The nucleophile is substituting. Here I have taken Y group as nucleophile and it is going to substitute X group. What is X group? Halogen, to give alkyl, the nucleophile of alkyl chain, and this X is going out as minus. So these nucleophilic substitutions are of three types, students. Unimolecular nucleophilic substitution, that is commonly known as SN1, and bimolecular nucleophilic substitution reaction, it is known as SN2, and intramolecular nucleophilic substitution reaction. Dear students, these two types SN1 and SN2 are very important with respect to their stereochemistry and their reaction conditions. Let us see one by one. For example, unimolecular nucleophilic substitution reaction. Let us learn first SN1. If I take SN2, you are going to confuse. So simply take tertiary butyl bromide or 2-bromo 2-methyl propane. It is nothing but this is tertiary butyl bromide. When I treat it with base, for example OH minus, what is going to happen? It loses bromide ion and gives carbocation. This carbocation is tertiary carbocation. It is going to be stable. Yes, its bromide ion is going out, and now when this tertiary carbocation is free, now this OH ion can attack from this side or from this side. So from wherever it wants, it can enter. So it is going to give alcohol. The stereochemistry and orientation we are going to learn in detail now. Yes. So in a similar manner, stereochemistry of unimolecular nucleophilic substitution reaction. What is happening? Since it is forming carbocation, let us say R1, R2, R3 are different compounds or different groups, and it is chiral compound. If it is a chiral molecule, chirality, I am going to explain what is chirality and optical activity in this video itself, right? So if it is tertiary alkyl halide and it is chiral compound, optically active compound, when I treat it with OH, so what is happening in first step? It is the slowest step where it loses chloride ion to give tertiary carbocation, which is an intermediate. It is stable intermediate. Now it is going to react with OH minus, where it can attack from this side to give this thick line, right, above the plane, right, or it can attack from this side below the plane to give this one. So the probability of attacking OH minus to this carbocation is 50-50, isn't it? 50% and 50%. So we are going to get a mixture of 50% of one isomer and another isomer of 50%. Yes, so the 50-50 mixture is known as racemic mixture. Yes, so where do you find this type of reactions or SN1 reactions? Where or which type of molecules undergoes SN1 type reactions? So the name is SN1, but what is happening? Simply it is substituting. Halogen is substituted with OH group. But the stereochemistry is, it is going to give racemic mixture. Yes, it is a two-step mechanism. What is happening? It is first step and this is second step, isn't it? So in first step, which is a slowest step, so losing this chloride ion is a slowest step and it is a rate determining step. Right, students? So there is a one story. What is rate determining step? For example, if you take car manufacturing unit, yet so while preparing or making a car, let us say it involves 10 steps. So the first step, if it is preparation of body, yes, it easily takes place, and the second step is going to be making of engine, and third step is going to be some other parts, or finally it is going to be colored, right? If the making of engine is the slowest step, so even if you make 100 cars per hour here, first step, and here also you have the efficiency, but the making of engine is going to take place only 10 cars per day, then what is the rate determining step? So this is going to be the slowest step, which is making of engine is going to be the slowest step, which is the rate determining step in a similar manner. So in SN1 type reactions are nucleophilic. S stands for substitution, N stands for nucleophilic. Unimolecular means, so this slowest step is the rate determining step. This step is based on, or it is depends on the rate of the reaction, depends on only the concentration of this starting material. So this reaction, since it is depends on the rate is going to depend on one molecule, so it is unimolecular. That is why SN1. Then where it undergoes, where do you find? Usually tertiary alkyl halides. It usually takes place tertiary alkyl halides, and secondary some extent, and primary usually you will find SN2 type reactions. So this is SN1 type. Tertiary is going to take place in tertiary alkyl halides, but not in primary alkyl halides. Yes, students, are you clear? So this is all about SN1 type reactions. So what is this racemic mixture? I am going to explain. Let us take allylic and benzylic halides. Yes, so yesterday I explained what is allylic halogen and benzylic halogen. So these allylic and benzylic halides show high reactivity towards SN1 type reaction. Why? Because this carbocation which is going to be formed, so for example this is a starting material, chlorine or bromine. When it loses minus chloride, it is going to give allyl carbocation. If you remember, benzylic carbocation is more stable than allylic, then tertiary. Yes, allylic. So this is a stability order. Allylic carbocation is more stable. So this stability is because of this this resonance with this double bond. Double bond is resonantly stabilizing this carbocation. So since it is going to resonantly stabilize carbocation, it will wait till the OH comes. Yes. So this OH is going to be give either of two isomers. So when it comes to benzylic position, yes, benzylic carbocation. This is the benzylic carbocation. It is also resonance stabilized with the double bonds of aromatic ring. So allylic and benzylic compounds also undergoes SN1 type reaction. SN1 type reactions usually you will find in tertiary carbocations or tertiary alkyl halides, and second one is allylic and benzylic halides. Yes, so this is usual pattern. Let us take SN2 reactions. So SN2 reaction is also similar to SN1. However, the step which is going to be substituted is a single step where the removal of halogen and incoming nucleophile takes place in one step, where this intermediate is a transition state. This is a transition state, we say. So during the transition state, the carbon is attached to 5 atoms. Yes, so 5 atoms it is going to attach, right? So from one side it is going out, and another side at the same time simultaneously it is attacked by OH minus to give inverted product. If the starting material is chiral compound, inversion takes place. This inversion is known as Walden inversion, because this inversion was first observed by Walden. So Walden inversion takes place in SN2 reaction. Walden inversion takes place in SN2 reaction. Why it is SN2? Bimolecular, because the rate determinant stepping is depends on incoming nucleophile, that is OH minus or other nucleophile, whatever the reaction you are going to do, and this is the substrate also. Since it is depending on 2 molecules, 2 starting materials, that is why it is known as SN2. So in a pictorial way, yes, it is coming, red ball is OH minus if I say. So it is simultaneously losing halogen, and this is going to be attacked, OH minus is attached. So what is happening? So one side it is going out and another side it is coming in. So is there any mixture? No, single compound we are going to get. Single compound we are going to get, isn't it? So single compound since we are getting, and which compounds usually it is possible? So for example, if I take, it is a primary alkyl halide, but it is substituted with 4 different compounds, 4 different groups. So one is chlorine, one is deuterium, another one is say ethyl or whatever with the alkyl group, and this is hydrogen. Since 4 groups are different, it is optically active. When I react this molecule with KOH, inversion is going to take place. What is inversion is going to take place? This chlorine is thick line, isn't it? And this hydrogen is dotted line. What is happening? So this OH incoming nucleophile is coming from back side, and it is pushing this hydrogen towards this side. So this hydrogen is here, and OH is coming into this room or this back side. So it is substituting in one step this hydrogen, this chlorine with OH, and this chlorine leftover place is taken up by this group or whatever may be the group present here. So if it is hydrogen, yes, it is hydrogen. Yes students, so this is how you are going to get only one product 100%. What is happening? So mechanism, it is going to take place transition state, and since it is a single step, this is known as concerted mechanism, and the inversion is what I said, Walden. Sorry, previously I wrote it as Walden, so it is Walden inversion. Yes, so Walden inversion, this inversion is going to be named as Walden inversion. What is inversion retention? I am going to explain in this video itself. Incoming nucleophile attacks from opposite side of the leaving group, it known as inversion. It was detected by Walden. So this SN2 reaction takes place with Walden inversion. Then where do you find? So this type of SN2 reaction is observed in primary alkyl halides, primary, whereas SN1 is tertiary, SN2 is primary. Yes, So to in a single step to come this OH minus, it requires free space. If it is already some substituted compound, it will not allow this OH minus to come inside. So that is why the primary alkyl halides undergoes SN2 reaction. Clear, students? So the differences between SN1 and SN2, these are very important with respect to your board exams. And if you know the concept, then only you can solve in JEE mains or NEET exams also. So this SN1 reaction takes place in tertiary alkyl halides, and this is primary alkyl halides SN2. And it is a two-step. SN1 is two steps, and SN2 is only one step. And first step is slow step and rate determining. And since it is only one step and it is a concerted reaction, rate is proportional to concentration of alkyl halide, whereas SN2 its concentration of alkyl halide and alkali, and this is unimolecular, whereas SN2 is bimolecular. And non-concerted means it is a two-step process, whereas this is concerted mechanism. Independent of concentration of alkali, these are all important, students. That is why I am reading all points. And it dependent on concentration of both. Carbocation intermediate is formed, isn't it? So tertiary carbocation was formed, right? Takes place via only transition state. You will not find any carbocation. Racemic mixture is formed, whereas Walden inversion is going to observed in SN2 reactions, right? Favorable in protic solvents. So usually you will use protic solvents like water, DMF, water, formic acid or acetic acid, and aprotic solvents like DMF, DMSO is used for SN2 reactions. Order of reactivity, it is important, students. If you want to react the substrate under SN2, yes, it should be tertiary compound, and if it is secondary, the reaction order will be shifts towards SN2. And order of reactivity, when it comes to SN2, it is observed in primary alkyl halides, and it is rare to find this SN2 type reactions in tertiary alkyl halides. Rearrangement may take place. Yes, so rearrangement may take place. So if you take allyl halides, right, allyl halides, or during, if you remember, during this isopropyl chloride, sorry, if you remember in propyl chloride and do Friedel-Crafts acylation, and it is going to form carbocation. This carbocation is going to be rearranged to secondary carbocation to give secondary carbocation. So this is how the substitution is going to, electrophilic substitution is going, this is different anyhow. So the rearrangement may take place, right? No rearrangement takes place in SN2 reactions. This is what is going to happen in SN1 and SN2. Clear, students? If you have any doubts, please post your doubts so that I will clear you. Next, an intramolecular nucleophilic substitution reaction, where this, it is not related to your alkyl halides, but since we are learning nucleophilic substitution reactions, so SNI is also one of the important reactions of organic chemistry. That is why I included here. Retention of configuration means what is happening with respect to this OH when I treat it with, yesterday we learned in previous lecture, are preparation of alkyl halides. Yes, it is stereoselective reaction, where if the starting material or alcohol is optically active, and this thick line OH is substituted with thick line chloride. Yes, so this writing of wedge shape and seesaw shape, all you have learnt in previous classes, isn't it? So how it happens? So this is the reaction mechanism, where in one step or first step it loses HCl, and this chlorine and removal of this oxygen or thio compounds SO2, and substitution with chlorine takes place via this transition state, where retention of configuration is going to take place. Retention means whatever the starting material stereochemistry is there and the product also is having the same stereochemistry, then it is said to be retention of configuration. Let us take in the following pairs of halogen compounds which would undergo SN2 reactions faster. So what is the carbon here? It is a primary. Primary carbon easily undergoes SN2. And what is this? It is secondary carbon. This is secondary carbon. So SN2, is it possible? No, this is not undergoes SN2. It undergoes SN1 type mainly. So when it comes to alkyl iodide and alkyl chloride, which is going to lose iodine easily or chlorine easily? Since the molecular weight is very large, yesterday I explained the bond length between chlorine and iodine, which is more. So bond length in alkyl halide and iodine is more, so this iodide easily goes off, and whereas iodine is a better leaving group because the bond length is very high compared to chlorine. Because of its large size, it will be released at a faster rate in the presence of incoming nucleophile. Right, students? So this is first one undergoes easily SN2, and iodide compound undergoes SN2 reaction faster. There you have some examples. Predict the order of reactivity of the following compounds in SN1 and SN2 reactions. The 4 isomeric bromobutanes. So this is primary and this is secondary, they have given, are benzylic, and here benzylic and with methyl group also is here. You can read here. So what is going to happen? The first compound, if I take, let me write, this is phenyl, CH2 and bromine. What they are asking? SN2 reactions. The following compounds in SN1 order. Let us write SN2, where primary, yes, it is primary, and this is right. So SN2 I am writing. SN2, order of SN2 I am writing. So what is the compound here? The 4 isomeric bromobutanes. Anyhow, here it is there 4 isomeric bromobutanes. Here it is given SN2 and SN1. I am solving this second one, right? So this is phenyl, CH, phenyl, and this is H, and it is bromide. Let us take other compounds also, we will come to know. So phenyl, this is the next compound, CH, and this is reverse of the SN2 going to be SN1. So this is CH3 and this is bromine, isn't it? And when it comes to phenyl, CH3O, it is tertiary, CH3, and this is phenyl, and this is bromine. So once you write like this, it will be easy. So we know that in SN2, primary alkyl halides easily undergoes SN2, right? So let us write primary first, then which is primary comparatively. So this is secondary, but it is benzylic. So let us write, this is compound 2, this is 1, 3 and 4. So third compound comes here, this is third one, then followed by second one, and followed by the fourth one. Yes. So the first compound SN2 reaction, because it is a primary or benzylic bromide, when it comes to, when you compare with these compounds, it may undergo, yes, what is the answer? SN2, yes. So this is what they have given. SN2 is, this is the compound SN2. Yes, phenyl benzyl bromide easily undergoes SN2 followed by CH3, yes, CH3 we have taken third one, and diphenyl methyl bromide, yes, second compound, yes, the prediction is correct, students. So this is the fourth one, which is diphenyl methyl bromide. This is how SN2 and SN1, where you will find different compounds, right? Stereochemistry, just now what I am saying, asymmetry, chirality and inversion and everything. What is chirality or stereochemistry? Symmetry. If you see symmetry, for example, take this ball, is it symmetric? If I cut to two halves, it is going to give two symmetrical objects. So this is some object with symmetry. If the molecule is superposable on its mirror image, is known as a chiral, not like hand. Hand is chiral. Hand is chiral. Yes. So these two hands are chiral hands. Though it looks like mirror images, but I cannot superimpose. I cannot put one hand over other. Right? If I put like this, so this side is thumb, this side is thumb. Is it superimposable? No. So chirality comes from the German word chirality means hand-like structures. Hand-like structures are known to be chiral compounds or chiral molecules. So you cannot overlap one hand on other hand, right? For example, if I take this ball or tree, if it is some symmetric object, it is going to be superposable. I can put this ball on this mirror image, so it is superposable. So it is achiral. It is not like hand. Symmetric objects are superposable with their mirror images, and symmetric molecules. So if I take this propanaldehyde, so this carbon is attached to two hydrogens, same two hydrogens, downside methyl, upside aldehyde, and the mirror image, since this hydrogen is same and this hydrogen is same, so if I put this blue color molecule over red color molecule, yes, I can put superposable. So this is achiral, and it is symmetric, isn't it? Symmetric molecule. I can cut like this, symmetric. So if I write O upside, I can write I can cut like this, symmetric molecule. So symmetric molecules are achiral. Symmetric molecules are achiral. Symmetric molecules are achiral. Achiral molecules are optically inactive. What is asymmetry? So asymmetry means which are not same. Two halves are not same. For example, if I take hand, so if I cut this single hand also, it is not same. And take this tree, asymmetric. This side is different, this side is different. And if I overlap this hand on this, mirror images are not superimposable. So chiral. So it is like hand-like structures. Chiral. So in previous example, this side also hydrogen. In this case, if I replace that hydrogen with OH, this aldehyde is going to be chiral compound, because if I replace since it is a mirror image, so right side I can say this, which side it is, OH is right side, and in this molecule it is left side, right? So if I lift this compound and put on this, or if I lift this molecule and put on this, what is going to happen? It is not superposable. I cannot put like this. I cannot put like this. And even if I rotate this total molecule in a clockwise direction or anti-clock direction, so this methyl is going to up and this CHO is going down, coming down. So I cannot put one over other. So this type of asymmetry is known as chirality. Chirality, right? Asymmetric carbon, the carbon which is substituted with four different molecules or four different groups, it is known as asymmetric. If it is substituted with four different, and moreover, if you thorough with this, if a chiral molecule has no symmetry elements of the Second type, mirror plane. It should not have mirror plane, that is sigma. SN1, center of inversion, and S2, rotation reflection axis as S2N. Then that molecule is optically active. That molecule is optically active. Anyhow, so this optical activity I have explained in detail under stereochemistry chapter. Please go through that chapter. You will understand what is all these SN1 and these symmetry elements and all. Optical isomers. So compounds having same molecular formula, similar chemical and physical properties, but differ only in optical activity are said to be optical isomers. Let us take some example. What is optical activity? It is the physical property where a compound polarizes. The phenomena of rotating plane polarizing light is known as optical activity. So if I take the compound and dissolve in some solvent and put it in polarimeter, in polarimeter you will have sodium lamp, where ordinary light is going to have like this. The sodium lamp is gives like this, and we are going to put a nickel prism. This nickel prism gives plain polarizing light, single light it gives. When this single light passes onto sample, this is a sample where the sample is compound is dissolved in solvent, and this light when it comes out, and if you see from this side, this light is not going to be the straight line. It is going to be either rotate towards right side or it may rotate towards left side. If the rotation is towards right side, then it is known as dextro-rotatory, and it is denoted as small d, or you can denote it as plus sign. It is very, very important, students. Please pay the attention. You can write it as small d or plus sign. If the light is going to be rotated towards left side, then it is denoted as levo-rotatory, and it is denoted as small l, and it is written as minus sign. It is minus sign. Yes. So it is minus sign is levo, left side rotation. So this is chiral compounds are optically active, which it pass ordinary light through nickel, right. Optically active molecule is non-superimposable on its mirror image. All chiral molecules are optically active. Yes, these molecules have that capacity to polarize the plane polarizing light towards right side or left side. Yes, students. Next. So levo-rotatory are the compounds which polarizes the plane polarized light towards left are known as levo-rotatory, and the compounds which polarize right side are known as dextro-rotatory, and it is denoted as small l, and here minus sign small l, and here small d, which is positive sign. Yes, students. So don't confuse with capital D and L. So capital D and L are different notations given for Fisher projections. Yes. So these capital D and capital L don't confuse with small l and small d. So small l, usually small l, small d rarely nowadays are writing. You can write it as minus or plus sign. Yes, students. Right. What is the importance? Identify chiral, and now we know what is chiral molecule, which is substituted with 4 different groups. The compound is said to be chiral molecule. The chiral molecules are the compounds which have power to polarize the plane polarized light towards right side or left side based on their polarity, based on their optical activity or the capacity to polarization of light. Either if it is right side, then it is said to be dextro-rotatory. If it is left side, it is said to be levo-rotatory, isn't it? Let us see. So what is the question? Identify chiral and achiral molecules in each of the following pair of compounds. So let us take this carbon. What is the chiral? Is it chiral compound? Yes, this is different OH, bromo, methyl and hydrogen. 4 different groups. So this is chiral compound. When it comes to this compound, so these 2 bromines are same. It is not chiral. It is a chiral. Right? Let us take this compound. Hydrogen, OH, methyl and 1, 2, 3 propyl group. So it is chiral. What about this? So this hydrogen, this OH, but this side is CH2CH3, this side also CH2CH3. These 2 groups are same, so it is a chiral. This is chiral, this is a chiral. Let us take this. So methyl, bromine, ethyl, this side is hydrogen, so it is also chiral. What about this? Bromine, 1, 2, 3 propyl, and whereas this carbon is having 2 same hydrogens, 2 sides hydrogen, so this is a chiral. A chiral, a chiral and a chiral. Whereas this one compound, this one compound and this 3 compound or 1 compound is said to be chiral molecules. So chiral compounds are the compounds which are substituted with 4 different groups or atoms is known to be chiral compounds, and the chiral compounds are the compounds which have capacity to rotate the plane polarized light. Right, retention of configuration. What is happening? Retention of configuration. Yes, so what is configuration? It is the spatial arrangement of groups or atoms around the carbon is configuration. So what is the configuration? Yes, this carbon is on plane, and this, since we are writing with dotted line, it is below the plane, and this wedge projections or thick lines are above the plane. So the configuration is what is happening when I treat this alcohol with HCl. So we are going to prepare this chlorine halide we are going to get. So what is the configuration of this? Is it going to be disturbed in this reaction? This carbon is not going to be disturbed. So in this reaction, the configuration is going to be retained. So that is why this is known as retention of configuration. Clear, friends? Retention of configuration. If the reaction, during the reaction, configuration is not disturbed, then it is said to be retention of configuration. Next, inversion of configuration. What is happening during SN2 reactions? SN2 reactions, it is undergoing inversion of configuration. So inversion means inside out. So the hydrogen which is inside or downside, it is coming this side, right? Which was left side, it is coming right side, and whereas these methyl or propyl, these groups are intact. So this hydrogen is coming this side. So inversion of configuration is taking place in SN2 reaction. This inversion is known as Walden inversion. So inversion inside out or opposite direction is going to take place. And is it chiral molecule? Let us see. Yes, this carbon is attached to hydrogen. This side bromine. This is cyclohexane group, and this side is methyl group. So 4 groups are different or atoms are different. So it is chiral molecule, right? So what about this? What about this? So this is also substituted with 4 different compounds or groups. So this is also chiral molecules. So what is happening? Inversion of configuration. Dear students, in previous examples you may say that here retention, it is minus sign and it is plus sign. So this rotation is irrespective of this configuration. This rotation is dependent on some factors. So this rotation may change with respect to solvent. Yes, don't worry about this plus sign and minus sign. Yes, so these signs are denoting the the optical activity, optical rotation. It is optical rotation is positive, dextrorotatory. This is levorotatory. Yes, so configuration, when it comes to DL configuration, you will come to know DL will not change. Retention of configuration, DL notation will not change. Anyhow, that I will explain. I have explained in different video. Please go through that. Right. So chiral inversion is taking place in SN2, whereas racemisation, yes students. So imagine you have one compound with dextrorotatory 100 degrees dextrorotatory compound in your hand, and you have left side rotating compound 100 degrees, same compound with different rotations. So if D compound is towards right side and L compound is towards left side, if I mix two compounds in one plate and if I measure the rotation, what is the rotation? It is going to be 0. This compound wants to turn to this side, this compound wants to polarize this side. So these two equal ratios will make it as 0, right? So it is going to be 0. The compound which is going to be obtained from SN1 reaction, for example, this is a chiral compound, isn't it? So what is going to happen in first step? It is two-step mechanism. First step, carbocation is obtained. So what is the carbocation here? Yes, this is the carbocation. So this carbocation can allow this incoming nucleophile from above the plane, yes, above the plane, or it can allow the OH from below the plane, right? Rear side or front side. It is also known as rear side and front side. So it can attack from both the sides. So if this OH comes from this side, it is going to give plus butanol, and it is going to give, if it is comes from downside, it is going to minus butanol, right? But is it possible to separate these two in one reaction? No, there are other methods how to separate these two molecules. Yes students, so that is different. So what is happening in one step? You are going to get plus, I can write plus and minus, two compounds I am going to get, mixture of plus and minus butanol. I am going to get butane 2-ol. So to denote racemic mixture, you have to write plus and minus in one over the other. This is a way of writing racemic mixture, where plus and minus, since you are going to get mixture of these two compounds, it is a racemic mixture. Racemisation of configuration is taking place. Yes. So there are methods to separate these chiral compounds. So there are other methods, right? Next. So this is how nucleophilic substitutions are two types, SN1 and SN2. SN2 is Walden inversion. Remember students, SN2 Walden inversion takes place in primary alkyl halides. SN1 is going to give racemic mixture. It is a two-step mechanism. It is going to give racemic mixture and racemisation takes place, and it is a two-step mechanism and bimolecular. It is a unimolecular reaction and two-step reaction. Clear students? So these are the major differences, SN1 and SN2. Don't confuse. So whenever you see alkyl halide, simply substitute nucleophile. If it is OH, substitute. When it comes to stereochemistry, then think, if it is tertiary alkyl halide, then it undergoes SN1. Tertiary undergoes SN1, and primary alkyl halide undergoes SN2. Yes, primary, it is free to allow incoming OH minus easily, because it is a primary carbon, the space is very high, so it can allow in one step, right? So SN2 is one step, SN2 is one step. Please remember, SN2 is one step or concerted reaction. SN1 is a two-step mechanism, unimolecular but two-step, where incoming nucleophile comes later after the formation of this carbocation. Yes students, this is how HaloAlkanes undergoes nucleophilic substitution reactions. Let us take elimination reactions. Elimination reactions. So the hydrogen which is attached to beta to this carbon, if the halogen is to this carbon is said to be alpha halogen, alpha carbon, and this is the beta carbon. The beta carbon, if it has hydrogen, it undergoes elimination reaction. Yes, elimination reaction. Elimination is what is happening. So this halogen is going out to give alkene. Elimination reactions also, it undergoes, alkyl halides undergoes elimination reaction. Yes, alkyl halide, when I add some base, strong base, it gives alkene. So pent-2-ene, if I react with base, yes, this is bromo compound, 2-bromopentane, it is going to give 81% of this side alkene. Here one point is there, students. So the point is Sage-Jeff's rule. Sage-Jeff's rule. Sage-Jeff's rule. So this rule states that, yes, this rule states that during the elimination, the hydrogen will be removed from the highly alkylated carbon. So based on this Sage-Jeff's rule, it is going to be formed as major, whereas this one alkene is going to be pent, one ene is going to be only 19%, whereas this pent-2-ene is going to form as 81 major product. Let us see the mechanism. You will come to know the detail. So elimination reactions are two types, students. Elimination reactions are two types. One is alpha elimination and second one is beta elimination. So alpha elimination reaction is where two atoms are going to be removed from the same carbon. For example, if I take chloroform and treat it with base, it is going to lose chlorine and chlorine to give dichlorocarbene. Dichlorocarbene is going to be formed. So this is alpha elimination reaction. Alpha elimination reactions are very rare. Yes. So very few examples you will find alpha elimination. Then it comes to beta elimination. What is happening beta elimination? So the hydrogen which is attached to beta carbon is going out as with halogen HX to give alkene. Clear? However, these beta eliminations are three types, similar to SN1, SN2, SNI. So these elimination reactions are also three types: unimolecular elimination reaction, bimolecular elimination, and elimination unimolecular via conjugate base. What is happening unimolecular elimination reaction? Yes, so in slow step, this is unimolecular. It loses halogen first to give carbocation intermediate. This carbocation intermediate then slowly loses this hydrogen to give alkene, and which is a first step. This is alcoholic KOH. So elimination takes place in presence of alcoholic KOH. Substitution takes, dear students, please note down this. Alcohol, alcohol, KOH, elimination reaction. Whenever you see alcoholic KOH, alkyl halide, alcohol KOH, alcoholic KOH, ALC, this like this, alcoholic KOH, elimination to give alkene. Elimination takes place. Whereas if it is aqueous KOH, aqueous KOH favors nucleophilic substitution. Please remember or note down this. Aqueous KOH, nucleophilic substitution takes place. Yes. So alcoholic KOH and nucleophilic substitution. Yes. Aqueous KOH undergoes nucleophilic substitution. So what is happening? This HX is going out to give alkene. Rate of reaction is proportional to the this alkyl halide. So that is why it is known as unimolecular elimination reaction. Then bimolecular elimination reaction. What is happening in bimolecular elimination reaction? In bimolecular elimination reaction, this incoming OH is going to redetermine where the rate of the reaction is going to be dependent on both the reactants. This OH is going to take out this hydrogen, and this is going like this, and this chlorine goes out like this. So transition state, it is going to be Like this, rate of the reaction is dependent on two molecules, so it is going to give these compounds. Just now what I said, E1, that is elimination versus SN1 SN2. So aqueous KOH, what is happening? Nucleophilic reaction. And alcoholic KOH, elimination is going to take place, right? When aqueous KOH is taken, primary alkyl halide SN1 reaction takes place. So please take down or note down these, students. So when I take aqueous KOH, primary alkyl halide, if it is primary alkyl halide, it undergoes SN1 reaction. When alcoholic KOH is taken, primary alkyl halide, elimination reaction takes place. That means SN1 usually observed in tertiary alkyl halides, isn't it? If SN1 reaction is going to take place, aqueous KOH, it undergoes SN1, otherwise it undergoes alkyl. So simply, not to confuse, alcoholic KOH elimination, aqueous KOH substitution. Yes, elimination unimolecular via conjugate base. What is happening? The conjugate base which is formed during the reaction, it is going to be formed base, so it takes out H plus ion to give this carbanion, and this base is slowly loses this fluorine, and this reaction is known as elimination unimolecular via conjugate base. So what I said, elimination versus substitution. So since we are taking alkyl halide and reacting with base, so if you take the bulky base potassium tertiary butoxide, for example it is potassium tertiary butoxide, it undergoes elimination. If it is simple sodium methoxide or potassium methoxide, sodium methoxide or potassium methoxide, it undergoes substitution reaction. So this base is going to attack easily because these groups will allow this linear molecule very easily to substitute. It allows to enter into the molecule, whereas this is already bulky. It will not allow this bulky tertiary butyl group into the molecule. So elimination takes place. This ion easily takes up this proton, beta proton, yes, to give this double bond, and this bromine goes out. So this is the beauty of this elimination versus substitution. So when you are doing alkyl halides, when you are treating with base, so you have to remember whether it is going to undergo elimination or substitution. If you want elimination, use tertiary butyl potassium ethoxide, potassium tertiary butoxide. If you want substitution, you can use the substituent whatever what you want to substitute. Yes, students. HaloAlkanes reaction with metals. So that type of reactions HaloAlkanes undergoes is reaction with metals. So usual reaction is Grignard reactions, where alkyl halides or aryl halides, when it is treated with magnesium metal, magnesium, it is easily available magnesium turnings, and take the compound in dry ether, because it should not have, it must not have water molecular moisture, because that water is going to generate this alkane back, right? So this alkyl Grignard reagent is prepared from alkyl halides with magnesium in dry ether. So please remember, students, alkyl magnesium halides are known as Grignard reagent. What is Grignard reagent? Alkyl magnesium halides are Grignard reagents. So what is happening? This R group is going to be negatively charged or nucleophile. Yes. So when it comes to this CH3 CH2, what is the charge over here? This is positive charge. So this R group is positively charged in starting material. In alkyl halide, the R group is positively charged. If I want to make it negative, what I have to do? Simply treat it with magnesium to give RMGX. So this magnesium is highly electron positive. This R group is going to turn it as nucleophile. So electrophilic carbon group or carbon atom is changed to nucleophilic carbon. Yes. So this is the beauty of metal reagents. So for example, magnesium alkyl magnesium halides are Grignard reagents. So what happens if you have water molecules in the reaction? This H plus ion replaces with this H plus minus. So H plus it easily takes up to give alkane, and magnesium hydroxide and chlorine will be goes out. So avoid water in the reaction mixture. What is going to happen? So this alkyl magnesium halide reagents usually reacts with carbonyl compounds, where these carbonyl compounds undergoes nucleophilic addition reaction, where this alkyl group is going to be nucleophile. So this nucleophilic addition takes place to give alcohols. Yes students. Next, Woods reaction. So Woods reaction, when you treat alkyl halides with sodium metal, it is going to give dimer of this alkane. So if it is this, for example, if it is propyl bromide and 2 moles, you are going to get 6-membered ring, 6-membered chain, 1 2 3 1 2 3. And if it is butane, 1 2 3 4 5, a 5-membered compound, and add 4-membered carbon with X, you are going to get octane, 1 2 3 4 5 6 7 8, octane ring. And in 2020 NEET there is a question, why don't you is it possible to prepare odd membered carbon chain compounds through Woods reaction? Odd member they have given 1 2 3 4 5 6 7 membered, 1 2 3 4 5 6 7 membered chain. Is it possible to prepare through Woods reaction? No, it cannot be prepared, because you cannot react with 2 different halogen compounds. If you take these 2 compounds in one vessel, if you want to make this odd member heptane compound, you have to take this propyl halide and butyl halide in one reaction vessel. So what is going to happen? You will get this heptane, but major compound you will get as this hexane and octane also. So you are going to get mixture of these 3 compounds. So usually odd carbon containing, odd number carbon containing compounds are not usually prepared through Woods reaction, because it is going to give mixture of compounds. This is how. So HaloAlkanes undergoes nucleophilic substitution reactions, SN1 and SN2, and other type of reactions these compounds undergoes is elimination reactions, and the metal reactions or Grignard reactions and Woods reactions are worth to read under these reactions. Dear students, in next video we are going to learn aromatic reactions or reactions of aromatic halogen compounds, that is reactions of HaloArenes. Under that topic you are going to learn nucleophilic substitution and replacement by hydroxyl group. Yes students, we will learn aromatic halogen compounds. Till then, bye students, thank you for watching. Please subscribe my channel Venus Academy if you are not yet subscribed, and don't forget to click on like button and bell button. We will meet again with aromatic halogen compounds. Till then, bye, take care, have a nice day. Good night students, since it is night. Yes, thank you, arigato gozaimasu, bye, sayonara.